Hello viewers, I'm Kausalya. Today we are going to discuss about oral decaying transients. So again this is the basic circuit diagram and this circuit has two positions. One is position 1 and another one is position 2. So initially the switch K is connected to position 1. Therefore a current I flows through this circuit. When the switch is held in position 1 for a long time, then the current reaches its steady state value. So the steady state value of current is given by E by R. Right, E is the source voltage and R is the resistance which is present in the circuit. Right. Now we are moving this switch K from position 1 to position 2. So this happens at a time T dash. Right. So now again we are going to apply KVL for this part. Okay, now the switch K is in position 2. So when you apply KVL, what happens? There is no voltage source, right? Therefore it is 0, and again we have to write expression for this R and L. So when you write expression, you see here it is I into R plus L into di by dt dash, which is equal to 0, right? Because there is no source voltage when the switch is connected in position 2. Now we are going to take Laplace transformation. So it is I of s into R plus L into s into I of s minus I of 0 plus, which is equal to 0. So here I of 0 plus is nothing but it is the steady state current. So which is given by E by R. Right. Now replace this I of 0 plus by E by R. So when you replace it, we are having an expression like this. Now here I am taking I of s commonly outside. So when you take I of s here, we are having R plus Ls, which is equal to Le by R. Right? Or in other words, we can write L into I. So again, when you find value of I of s, so I of s is given by Li divided by R plus Ls. So here again in the denominator part I am taking L commonly outside. So both the numerator and the denominator L cancels each other. And finally our expression is I by S plus R by L. Right. Now we are going to take inverse Laplace transform because we know we have to find the value of I of t dash. So inverse Laplace of I of s is nothing but your I of t dash, right? So here I remains as such, and s plus r by l, when you take inverse Laplace transformation, it becomes e power minus r by l t dash, right? So here when you replace r by l is nothing but 1 by capital T. So our final expression comes like this, right? Next we are going to draw the graph. Right, graph between your t dash and I. So here we have to substitute the random values of t dash and we have to find out the value of I. So here it is decreasing, right? Now the next thing is we have to find the voltage drop across your resistor and inductor. So voltage drop across the resistor is given by I into R, right? So R you just write as such, and for I we are having an expression I into e to the power minus t dash by t. Similarly, ER is nothing but, you see, I into R is E, right? So E into e to the power minus t dash by capital T. Next, we are going to find the voltage drop across the inductor. So ER plus EL is equal to 0. Therefore, EL is nothing but, when you move this ER to the right hand side, it becomes minus ER. So this is your expression for EL, right? Now, we are going to draw the graph for the voltage drop across the resistor and inductor versus your time t dash. So here when you draw the graph, again you have to select the random values for t dash, right? And then you have to draw the graph, and here we are having a graph like this, right? Now the next thing is we have to find the time constant for decaying transients. So here the time constant is again what is the expression for I of t dash. Here this is your expression, right? So in case when the exponential term, okay, for this entire term if you are having the value of 1, it is I into e to the power minus 1. So e to the power minus 1 is nothing but 0.368 times of I, which is nothing but 36.8% of the initial value, right? So here comes the end of this derivation. If you have any doubt, let me know in the comment section. Thank you.